Hello guys, today I want to talk how to measure time. The tool we want to use is spring circuit. So let me show you our idea. Introduction. I will tell something about spring, like the underlying phenomena. What are the parameters of the problem? In this section, I want to explain that what other parameters can affect spring vibration. Because the method we use to measure time is see how many times the spring vibrates. In the next section, I will talk to degree of freedom system, and then introduce what is the engineering relevance, and finally, the plan. First, what is spring? Not this spring, it's this. A spring is an elastic object that stores mechanical energy. Springs are typically made of spring steel. There are many spring designs. In everyday use, the term often refers to coil springs. The picture is coil springs, which we often see and use. What is the underlying physical phenomena of spring? By Hooke's law, we know that F equals minus kx. X is the displacement vector, the distance and direction the spring is deformed from its equilibrium length. F is the resulting force vector, the magnitude and direction of the restoring force the spring exerts. K is the spring constant of the spring, a constant that depends on the spring's material and construction. The negative sign indicates that the force the spring exerts is in the opposite direction from its displacement. And then we make F equal ma, which A equals the second derivative of x with respect to t. And then put all parameters to right. So we get the second order of ODE. Like the picture illustrates, the spring can vibrate in a constant period. If we know the parameter of the spring, theoretically we can calculate the time by see how many times the spring vibrates. The solution of ODE is this. A and B is an arbitrary number. There are some important properties of spring, like frequency and period. First is omega, this, and then period t. Last is frequency. So we talk a little physical phenomena of spring. However, the formula is not complete. It should be like this formula. We add a parameter which called damping ratio. Use symbol zeta. Zeta is this. Why we add damping ratio? Or what is the function of damping ratio? The damping ratio characterizes the frequency response of a second-order ODE. In general, the system with higher damping ratios, 1 or greater, will demonstrate more of a damping effect. The damping ratio provides the level of damping in a system relative to critical damping. Zeta equal actual damping divided by critical damping. And critical damping is relative with M and K. We get a new ODE. And how does the spring vibrate by different zeta? There are 4 situations: undamped, underdamped, overdamped, critically damped. First, we talk about the situation of undamped. Undamped is the case where it corresponds to the undamped simple harmonic oscillator, and it vibrates like the video. Second is underdamped, occurs for zeta between 0 and 1. And this is video. Third is overdamped, occurs for zeta greater than 1. So this is the video. Last is critically damped, occurs for zeta equal to 1. Okay, let's summarize the parameters of the problem. The formula of second order ODE is this, and other parameters like M, mass, K, the spring constant, X, the displacement vector, and damping ratio, or called zeta, is actual damping divided by critical damping. So if we know the parameter of the spring, we can measure time. Okay, I want to talk 2 degree of freedom system. Let's see the figure 1.1. This is a simple 2 degree of freedom system. It has 2 springs and 2 mass. How to get x1 and x2? Newton's law can be applied to the system in figure 1.1 to derive the equations of motion. The steps are omitted for brevity. The resulting pair of ordinary differential equations can be represented in matrix form and are coupled via the damping and stiffness matrices. So let's talk about engineering relevance. Let's see left picture. Springs are a vital part of a suspension system. Without them, you will feel every bump and carry you roll over. Most vehicles are equipped with coil springs. The job of coil springs is to absorb the shock force we encounter when driving over a bump in the road. By compressing and recoiling back and forth. When we drive, we feel little movement because the springs are doing their job. When springs begin to fail, it's usually caused by constant overloading, excessive use, or just a general breakdown of the metal. Springs will also rush out, especially in cold days because of your salty roads during the winter. Another tool is spring scale. A spring scale is a type of mechanical force gauge or weighing scale. It consists of a spring fixed at one end with a hook. the hook to attach an object at the other. Because the spring is worked by Hooke's law, the force needed to extend a spring is proportional to the distance the spring is extended from its rest position. In the end of this presentation, I want to talk the plan. First, we will get a parameter of two springs, include mass, K and C. Next, we use Python to get a period, and the picture is template idea of our tool to measure time. This is our reference. Thank you.
This is 2 degree under damp spring mass system by Python. First, I set the data of spring constants, damping coefficient, mass, initial displacement, and initial velocity. Since the damping reaction is equal to damping coefficient, divide by 2 multiply square root of mass multiply spring constant. The damping reaction is lower than 1 in this system, so the system is underdamped. To make my graph more smooth, I set data of time in 10 seconds and divide it into 10,000 parts. Then I initialize the array of displacements, velocity, acceleration for cos 1 and cos 2 and set the data for that. The most important part is the formula of acceleration. It's the key of this program. Then to do the animation, I need the data of position for cos 1 and cos 2. So I initialize position 1 and 2 for cos 1 and cos 2. But I also need the data of original position. So I get the data of original position for cos 1 and cos 2 by position 0 for cos 1 and cos 2 minus displacement 0 for cos 1 and cos 2 and set the data for them. Then in realization, we will set the degree that this system cannot exceed it. For example, in this case, I set when displacement is not higher than 0.2, the clock is over and record. Then this part is for animation. So we can go to see the animation.